Okay, we are recording now. So goal for today is to continue with acoustics. And today we are going to look at the first 15 minutes, 20 minutes, we are going to look at another application of adaptive filter, but not in noise cancellation, but in vibrations, communications using vibrations. And we'll kind of quickly take a look at how adaptive filters are used in such kind of vibrations systems. And then we will talk about something fun, which is inaudible acoustics, acoustic signals that cannot be heard, but we can use them to actually attack things like Alexas and any microphones or any device that has a microphone. Okay, so that should have some video. So everything we're going to do is on slides today. There's no notes, so there's not that much amount of math today, but we are moving more towards applications of things that we've already seen. So today will be a day of applications. But I think the second part would be fun because it says, hey, we can do all illegal things or all kinds of attacks on different stuff. And doing illegal things is sometimes fun. Yeah. Okay, so let's get started. Let me share my screen. Any questions thus far? Guys, any questions? Okay, good. Let's get started. Okay. Again, thanks very much for sharing your screen, for turning on your video. If there are more people who could turn on during the lecture, great. If not, I totally understand. Okay. So guys, we talked about noise cancellation last class, and I hope you saw how we are paying a lot for the sponge, right? That's one summary of what we saw last class, but the more important summary, by the way, that sponge is a very carefully designed sponge. But the other summary was, oh, adaptive filtering can do pretty interesting stuff. But one of the issues with adaptive filtering is that when you do not have too much of time to really compute the autocorrelation matrix of the source signal or the cross covariance matrix of the source and the reference microphone and the feedback microphone signal, right? You cannot compute that cross covariance. So then we saw that adaptive filter said, okay, let's just take the instantaneous values and the multiplication of that. Let's think that's the approximation of the covariance. And then we saw this application where we had a wireless relay. In fact, that's a good idea. That's a good example of how RF and acoustics can be fused. It's like a fusion where the combination of the two gives you a look ahead. And because of the look ahead, you have this time buffer in which you not only can you do faster, not only do you have enough time to do the computation, it also allows you the time to compute that covariance kind of a matrix, okay? Because you can see all of that upfront. So that was one, noise cancellation was one application of adaptive filtering. Today we are going to switch gears a little bit and we are going to also look at vibration, okay? This is some work that has been done by some people in the research community. And the core idea is the following. So, okay, look, acoustics is nothing but vibration of the air, right? I mean, acoustics is also, you can think of the air particles vibrating, and because one layer of air particles vibrate, the next layer starts vibrating, and the next layer starts vibrating, and that's how the ripple effect kind of flows through the air, right? I mean, this is also similar to how you throw a stone in water, and there's a ripple in the water, right? So it's really vibrations through the air, right? Now, if it's vibration, then some people, including ourselves, we started thinking, okay, can we create controlled vibrations? In other words, can we program these vibrations? Okay. So that made us look into what is, okay, that made us look into not only acoustics, but also these piezoelectric vibrators in your phones and your watches and all these devices that buzz, right? Your phone buzzes when there's a phone call, right? So what exactly buzzes? Oh, there's this vibration motor. Can you see my cursor? Yeah. So there's this vibration motor almost in every device. In fact, interestingly, it's not only in smartphones, it's also in dumb phones, right? It's in your watch, it's in your Fitbit. Almost everything has this vibration motor. And the way it's utilized today is to give you an alert, to give you a notification, right? But it turns out this vibration motor, if you look inside it, it's a small magnetic mass that's actually suspended inside a metal coil. Okay, it's a magnetic mass inside a metal coil. And if you pass electric current through that coil, you know that there's going to be a magnetic field inside that spiral, inside that coil, right? Now, because of that magnetic field, the mass would actually move. Okay. Now, suppose you pass AC current, because the direction of the magnetic field would keep alternating, this thing would move back and forth. Okay. And now if it's moving back and forth, if you change the frequency of the AC current, if you change the amplitude, the magnetic field's oscillation would change, the swing would change. And as a result, the vibration that's created by that magnetic mass can now be thought of as a signal. Right? If you touch that vibrating mass, you will feel a vibration. And if you take the FFT of that signal, you should see a bunch of frequencies and magnitudes of that FFT. And maybe and a phase as well, depending on where the magnetic mass is starting from, that will be the phase. So you see, right, how we are connecting things from FFT to acoustics being vibration, to now a vibration motor, which just has a magnetic mass which is moving back and forth inside a coil. Right? So if you can connect vibration motor to an FFT, then you say, okay, why don't I start doing all kinds of communication and signal processing with it? Okay. So the idea is, okay, I can create this signal by controlling the current that I give to the vibration motor. I can create whatever signal I want, right? As long as the coil supports that signal, right? And that creates the vibration. And how do I receive the vibration? Any thoughts on how do I receive the vibration? I mean, I can touch it and feel it, but I want a signal, right? I want a real vector. I want real voltages on which I can take FFTs and on which I can maybe encode data. So what is a good receiver for a vibration?
Pressure sensor, I guess.
Pressure sensor. That's a good idea. But we don't have pressure sensors in our mobile devices, right? So by the way, what is a pressure sensor? Are there any known pressure sensors that you know of?
Like a weight measure kind of thing.
Yeah, sure. But yeah, that's true. But our phones, that's very much true. But those weight measures may not have that much sensitivity, right? Because these vibrations are going to be very small, right? Are there other sensors with which you can capture vibration?
Accelerometer.
Accelerometer, right? You take your phone's you do this experiment at home. Take the vibrating phone or your vibrating watch, take your friend's phone and touch it and see what your accelerometer does. The accelerometer is going to vibrate. It's basically going to pick up that vibration signal. Any other sensors that could pick up vibration?
Microphones.
Microphones, exactly, right? Microphones is picking up nothing but air vibrations, right? The air vibrations come and hit a paper, a diaphragm on the microphone, And once it hits the diaphragm vibrates. That's a form of a pressure sensor. Now, what if you touch the vibration motor on your microphone? The microphone's diaphragm is going to vibrate. Okay. So we have these sensors from which we can pick up vibrations. And so then the question is, can we start encoding data, bits, in these vibrations, and then pick up that data through a motion sensor, a vibration sensor, such as an accelerometer or even a microphone? Does that make sense? So if I tell you encode data in vibrations, what might you do? How would you encode data in vibrations? Morse code. What can you do with Morse code? Right? Easy thing to do is when there is vibration, that's 1. When there's no vibration, that's 0. Right? So if you have a bit string of 100111, you vibrate for a little bit of time. That'll be your symbol interval or your data bit interval. And then you don't vibrate for 2 time units, 100, and then again you vibrate for 3 time units. That's your Morse code. That'll give you some data, right? And your accelerometer will get some vibration signal, then it will be noise, vibration signal, and you're getting data out of it. Right? But you can do much better. Okay. What you can do is, you can take every frequency of the, let's say your bandwidth of your vibration motor is 16 kilohertz. Actually, it is true. But what is the bandwidth of your accelerometer? Guys, what is the bandwidth of your accelerometer? What sampling rate do you get out of your accelerometer?
It's around 100 kilohertz.
How much?
100 kilohertz. Or hertz.
Hertz.
Hertz, sorry.
Yes.
Feeling.
Was that Lucas?
That was John.
It was John. John, it's hertz. And
I don't know why I was feeling optimistic.
No, that's
today.
fine. That's totally fine. I confuse kilohertz and hertz as well. What is the sampling rate that you have been using for your MP? Do you know?
Yeah, 100 hertz.
100 hertz. Okay.
Yeah.
So 100 hertz is common, but you can also get 200 hertz in some of these good phones. Okay. Sometimes these, because accelerometer typically not being used for very fancy applications, they give 100 hertz. But I think in a gaming mode, or there's some mode in which you can actually make it 200 hertz. So you can get 200 hertz. And maybe there are some accelerometers, some special cases where you can get 500 hertz. Okay. So if the vibration motor, if the transmitter can do 16 kilohertz and the receiver can do 500 hertz, right? What frequencies can you use for communication? You cannot use more than 500 hertz. Right? If your receiver cannot receive it, what can you do? Right? So, okay, you take 500 hertz of this input signal, and for each frequency bin, you put a data 1 or 0, right? So let's say you divide 500 hertz into 5 bins of 100 hertz each. Okay. The first bin, you put 1. In the second bin, you put 0. Third bin, you put 0. Fourth bin, you put 1. Fifth bin, you put 1. And what does 1 mean? You say, okay, the frequency amplitude will be high if it's 1, will be very low if it's 0. Right? So I create a signal in which I have this bunch of 5 frequencies or 5 frequency bins. I make the first bin amplitude high, the second bin amplitude low, the third bin amplitude low, the fourth bin amplitude high, the fifth bin amplitude high, and that is 1, 0, 0, 1, 1. And I take these frequencies and I now take a IFFT. Right? I take these frequencies, each frequency is like a sinusoid signal, let's say. I amplify the weights of each of these frequencies based on that 1, 0, 0, 1, 1. And then I take an IFFT of that. An IFFT of the frequencies will give me a time domain signal. Guys, are you with me? Right? And now the time domain signal, I pass that as the current in the coil. Now what will happen? The magnetic mass is going to move in some weird ways, right? Depending on how the signal is going back and forth. Now you receive that signal at your accelerometer, right? And you take and then that signal, which is how the vibration happened, which is again a function of what signal you gave into the coil, right? So now you have the accelerometer date signal, and now you take an FFT again. What should you see? In those FFT bins, 5 bins, you should see the first bin having higher amplitude with some noise, of course. The second bin having lower amplitude, the third bin having lower amplitude, the fourth bin having higher amplitude, the fifth bin having higher amplitude. Of course, there's noise. If the noise is large, then you might think that the low amplitude is actually a high amplitude, right? So you might have errors. But if you're just saying 1 or 0, you can make the high amplitude much higher, the low amplitude much lower, and hopefully you will get that same effect at the accelerometer. And hey, then at every symbol, at every time window, you are getting 5 bits, right? So you've increased your data rate 5x over Morse code. Right? Because with Morse code, you're getting 1 bit every time window. Okay. Now the question is, okay, why should I do 5 bins? Why not I break the 500 hertz into 500 bins? Sure, maybe you can do that, but that means every frequency is now carrying data. Maybe there are problems with that, because if that frequency has some noise over there and the noise is large, you'll have a data error. You have a bit error, right? So you might say, no, I want a few frequencies to embody that one data bit so that I have some averaging effect for noise. Right? So now it's a design question. How can you push the data rate for vibratory communication, right? Given that your receiver is an accelerometer. Questions?
I just had a question about sort of like, I guess it's like Nyquist sampling rate.
Right.
Like, technically, don't we only have half of the frequency? Exactly. So it's only like 2 or 3 bins.
You only have 2. You basically, what you do is you say, okay, I have 200 hertz sampling rate at accelerometer. So I really have 100 hertz, right?
Okay. Okay. But yeah, I get the example though. Okay.
Exactly. Yeah. So you divide 100 hertz into 20 hertz, 20 hertz, 20 hertz, that's 5 bins. If you see that, you know what, 20 hertz, the noise characteristics of your accelerometer and of your vibration motor, that noise is too high. Maybe you want to increase the bin length because you want to average out noise. You know, now you do engineering, but you see what the idea is.
Okay, thank you.
Yep. Any other questions? Okay, good. So the point is, if I can do this, my first idea is to touch the vibration motor on the accelerometer itself, right? But hey, vibration also flows through conductive surfaces or any surface, right? So what if I have a vibration motor? What if I have a phone that's vibrating with this encoded data on one part of the table, and I have another phone on the same table, and one phone is vibrating? Will the accelerometer of the other phone pick it up? Right? If you can do that, then now you can imagine applications, right? Maybe a company would have a kiosk in which there's a table. The table is vibrating all the information about the company. You put your phone on the table, your phone gets all the information, you walk away. Right? I mean, there's a meeting, everyone comes to the meeting, they put their phone on the table, all the business cards get automatically exchanged between every pair. They take the phone and they know they get the business cards of everyone else. Now the question is, does this vibration also flow through your body? Do you think it flows through your body?
Yeah, of course.
Totally, it flows through your body, right? It flows very well through your bones. Okay, so you can potentially say that I'll wear a watch. My watch has my credit card information, and next time I go to do mobile pay, Apple Pay or Google Pay or whatever mobile pay, your favorite mobile pay, you don't have to take your phone out anymore. You just touch that point of sale device, right? And your credit card information flows through your bone. Okay.
This is sort of the reverse of what you're describing, but a couple of years ago, there was a successful, I don't remember who published it, there's a successful demo of sensing vibrations of someone typing on a laptop keyboard, like on a table, and using that information to get passwords.
Exactly.
They could detect keystrokes from the vibrations.
That's right. So this was another paper, and in fact, there are several other papers along that line. So the idea over there was you place your phone next to your laptop and you type on your laptop. Okay. And because your typing creates vibrations, and the vibration is coming from different locations, your phone's accelerometer can pick up those vibrations, and from that, maybe the way the vibration has attenuated, I mean, that was a machine learning problem, right? They didn't model how the vibration, they didn't localize the vibration, but they applied machine learning, and they could show that from the accelerometer data, you could pick up what the user is typing. Right? Because if your accelerometer is on the left side of the keyboard, when you type Q, the vibration is much stronger versus when you type P, which is on the right side of the keyboard. So from that, you can start doing some machine learning and say, oh, okay, strong vibration, weak vibration coming from an angle, blah, blah, blah. I can see what's going on. Right? And maybe use people, when they type Q, they have a softer force. When they type space, they have a higher force because of their thumb doing space. All of that, I mean, the machine learning algorithm learns all of that, right? And does classification. Okay. So now back to this vibration, you can now send your data through your bones. And then, we were talking with a bunch of companies about these mobile payment kind of applications, and they were very interested. But one of the concerns they had was, if someone stole my Apple Watch, the thief could essentially wear that watch and use my credit card everywhere, right? Do you have a solution around it?
Isn't it exactly the same if a thief were to steal your credit card? And
that is true.
The model doesn't really change.
That is true. In fact, it might be harder with the smartwatch because you'll notice it much quicker, whereas with the wallet, you might notice it much later, right? Right. So you're absolutely right. It's the same with the credit card. But these mobile companies want to improve security. It's not good enough to say this is as bad as a credit card. Okay. So the point, yeah, anyone wants to say something?
Okay. I was just gonna say, maybe you could try like using other sensors. Like, I don't know if a microphone is good enough, but I know some companies, when you call them, they can confirm if it's you with your voice. I don't know if that's practical for this, but I don't know, maybe like other sensors could be used.
Sure. I mean, there's definitely other sensors that you can do, right? You can do NFC, near field communication, etc. But if you just keep it to vibrations, one of the ideas that came up at that point in discussion with these companies was that when the signal flows through your bone, how do you model the received signal? The source signal convolved with a channel. Right? Your bone is also a channel, right? So then your received signal at the accelerometer, let's call it Y. Y is nothing but H convolved with X, where X is the source vibration signal and H is the bone channel. Right? And maybe the bone channel has multipath. Right? Maybe inside your bone, maybe the vibrations are one vibration is going along a straight path, another vibration is reflecting, like total internal reflection inside the bone. I do not know the bone channel very well, but one could pass an impulse through the bone and see what the bone impulse response looks like. Right? And that's the channel. And the thought experiment was, if people have different bones, different bone densities, different tissues, blah, 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 can you fingerprint that channel? And as a result say, okay, if Romit's smartwatch is worn by Lucas, even though the smartwatch is sending the same signal, Lucas's bone would be different, bone channel would be different. So the receiver should be able to say that this is not a legitimate transfer. Right? So then the question was, how can we design such a system? Right? And there have been thoughts around these, that can we exploit the fact that human bones might actually be a unique conductor, or at least reasonably unique. You need not be absolutely unique, reasonably unique channel. Okay? So all of these things that we are talking about, these courses, come together in these kind of new applications, which is vibration-based communication. Okay, very good. So then if you can do these kind of vibratory communication, right, then maybe there are various applications that can open up. And like I was saying, maybe you log in your smartphone into your smartphone just by touching it, not by any gestures or anything, but once you touch your smartphone, your smartwatch sends the signal. Okay. You might touch your car door and your car door opens. You might shake your hand with another person, and both of you are wearing these vibration-based arm wristbands, and maybe your business contacts exchange through the handshake. Right? Entirely possible. Right? And maybe you do credit card transactions just by touching. In fact, in COVID, in this COVID situation, at some point we were thinking it's important to understand whether people touch something, right? Whether you touched a doorknob, or how many people touched a doorknob, right? And the idea was, is it possible to send a vibration from your smartwatch or some ring, some wristband, and then if you do not touch something, the vibration flow through your fingers and maybe come back, right? I mean, somehow the vibrations are flowing through your fingers, right? So if you send a vibration from your watch and you also record what your accelerometer is picking up, you might see some reverse flow of vibrations, right? Because the vibration is flowing through your fingers. Whereas when you touch something like a doorknob, maybe the vibration pattern changes, right? So there was some thoughts in several research groups around, can we use vibration to understand what you touched, what you did not touch, how many times the doorknob was touched, and accordingly do sanitation in different places. Okay. So this vibration business is playing an interesting role, especially with touch becoming a new important primitive in the pandemic and post-pandemic era. Okay. Now, one of the issues when we were doing some of this research, one of the issues that came up was with accelerometer, you were getting around 400 bits per second. Okay, simply because the accelerometer bandwidth is pretty low. Okay. They said, okay, well, how can we increase the bandwidth? And I think the answer was, why don't we look at microphone? Because the microphone's bandwidth is how much? 20 kilohertz easily, right? And the vibration motor's bandwidth was 16 kilohertz. Great, right? Let's use the microphone. And the point was, we'll touch the microphone with our smartwatch vibrating. The signal V, that is the source signal, the vibration signal, will flow through the H bone. H bone is the channel, right? And the microphone would receive this signal, which is V convolved with H bone. And from that, I'm going to decode the signal, the source signal V. The only issue is, unlike an accelerometer, the microphone is susceptible to all the ambient noise in the room. So if you think of a coffee shop where you want to do mobile payments, there are other sounds in the ambience. That sound will also get picked up by the microphone, simply because the microphone's diaphragm vibrates to air vibrations, whereas an accelerometer does not vibrate to air vibrations. Does that make sense, guys? Right. So then if you think of the problem really becomes the signal that the microphone receives is the vibratory signal. I mean, I should really write this as V convolved with H bone plus the sound signal, which is the music that is being played convolved with the air channel, right? Music that is being played in the ambience, or like people talking convolved with the ambient channel. Make sense? So the microphone is receiving the sum of these two signals, but your aim is to separate the vibration signal from the mixture. This is a difficult problem. This is like saying, I tell you that the sum of two numbers is 10. Tell me one of the numbers. Right? It's very hard. Right? Because essentially what you're getting is a mixture of vibration and ambient sound. And now you have to decode what the vibration is, and you do not know how the mixture was composed. So, okay, this is hard. I mean, by the way, there are certain ideas in which if V and S, okay, have certain structures, if they're independent, for example, there are some statistical properties that they satisfy. It is possible to separate them. This is called independent component analysis. Okay? But we are not going to go there. This is, for example, if I say that two prime numbers added up becomes 12, then you might be able to say, the prime numbers are 7 and 5. Right? Because the prime numbers have certain properties that they satisfy. But we're not going to go there. We're going to say, okay, well, how can we solve this problem? So another idea over here, or one idea over here is, look, many of these devices, receiver devices, is like a smartphone, they have two microphones. In fact, a smartphone nowadays have 3 or 4 microphones. Okay. So if you have two microphones and you touch one of them, then you can think of the other microphone only getting S. And now the question is, I have S on a separate microphone. I have V plus S on one microphone. Guys, can you subtract? Can you subtract?
Not directly, I think.
Say that again?
Not, you cannot directly subtract that because there are some delays. Maybe you can shift one of the signals and subtract.
Okay, so how fun is saying, look, V plus S and S, you cannot immediately subtract because this right hand S is not exactly this left hand S because there is a delay. True. But the delay is not only the line of sight delay, right? There is multipath over here. Let me see if I can annotate. Oops. Hey, what happened? Yeah. There is multipath as well. Make sense? So your delay is not just your AOA, angle of arrival delay. It's angle of arrival in every different angle in which the echoes are arriving. Right? This is the same as our adaptive filter, where we were saying the feedback microphone's channel and the reference microphone's channel is not just one delay shift, it's a complicated difference. Right? So if you want to cancel, if you want to cancel, it's not an easy cancel. What does this remind you of? That noise cancellation. This is what, again, goes back to adaptive filtering. Right? This is your desired signal. Or you can think of, you can think of this is as your desired signal, and you want to subtract this desired signal from this signal perfectly. So what you really need to do is, if this channel is H1 and this channel is H2, you need to estimate H2 inverse H1. H2 inverse H1 of S2 is what? S2 is nothing but source S convolved with H2. So source H2. H2 inverse H2 cancels out. So it's source. And source convolved with H1 is exactly what you want to subtract from this. Does that make sense, guys? Great. That would have been easy, except in real phones, it turned out that these two microphones are on the same PCB, on the same circuit board. Okay. So when you touch one of the microphones, the vibration actually propagates through that circuit board to the other microphone. Okay. And as a result of that, once the two signals get correlated, adaptive filtering starts to fail. And we're not going to go in there, but one thing to remember just as a fact is that adaptive filter works well when these two signals are uncorrelated. So correlation derails adaptive filter. That's why things go down. And there's been good amount of work in figuring out how to kind of design modifications to adaptive filter so that they do better even in the presence of correlation. Okay. But we won't go into that. But the takeaway or what could be achieved is that it's possible to do 400 bits per second with accelerometers. But it's possible to get much better 8 kbps with microphones. And 8 kbps is from a finger ring. A finger ring, you know, these electronic finger rings could have vibration motors in them. So from a finger ring, you can get 8 kbps. From a smart watch to your fingertip, you can get 4 kbps. Of course, right? As you go further away, your bit rate is going to go down, right? Because the signal is traveling over a longer distance and the channel is attenuating the signal. Okay. So here is a demo, but let me first clear my screen. Wait. How do I clear my screen? Clearing my screen is annotate, clear. So here is a demo in which this person is wearing a finger ring which has a vibration motor inside it. Okay, you can see the vibration motor. Right? Can you see my cursor? Yeah.
Yes.
So this is the vibration motor. This is connected to a battery, which is not visible. And the vibration motor encodes this image of the Illinois logo, like an image. Okay. And now this laptop is connected to a microphone chip. You'll soon see it. It's behind the hand, behind the person's finger. And there are two microphone chips over there. It's going to do that adaptive filtering. And the goal is to basically transfer this picture to the laptop by touching it. Okay. So here you go. Okay. So you see, right, that didn't take that much time. It's around 6 to 8 kbps, but there are a bunch of errors. Right? Look at many of these blue points becoming white, and there are some white blue dots in the white parts as well. Because in any of these communication systems like Wi-Fi, etc., right, the receiver gives feedback to the transmitter saying this bit was an error. Can you retransmit the packet? Right? But in this case, there's no way of giving feedback. Right? It's a feed-forward channel. Right? The microphone cannot tell the vibration motor this bit was wrong, and therefore you need to retransmit it. Right? So you have to live with whatever errors there is. So that's a little bit of a challenge with your credit card as well, right? So there are some issues over here, but the point is, look, the picture got reasonably well transferred and it was reasonably quick. So one idea with credit card would be to send the credit card maybe 20 times and then take a voting across all those. For every 20 bits, right? The most significant bit, you have 20 bits, you take a vote and that's your credit card number. Okay, so this is all I wanted to say about vibration. Wanted to give you a kind of a high level sense of, oh, what are other applications of adaptive filters, and the fact that vibrations is potentially a modality for communication, which could make things interesting and open up new forms of personal peer-to-peer communication. I mean, you can exchange music files with each other just by touching each other's phone. Okay, questions?
Professor, do you mind just quickly, I know you said you didn't want to get into it, but could you just repeat what you said about correlation derailing adaptive filtering, why that happens?
Yeah, Lucas, it's hard to get into that without the math, but I think the way to look at it, one way to think about it is, if the signal that you're receiving and the signal that you want to cancel, they are correlated, means that they go up and down together. Okay. Then it's hard to estimate that minus H1 inverse H2. Because you can think of gradient descent as a way of searching, right? You're saying, if I do this, what happens? If I do that, what happens? And if it turns out that whatever you're doing, it doesn't matter much because the other signal and your signal, they're both jumping up and down the same way, you get less information by doing gradient descent if they are jumping up and down the same way. Whereas if they're doing the opposite things, then your gradient descent converges better. Let me see if I can think of an analogy.
That kind of makes sense, actually. It's like, it's almost like it has no effect on the signal.
Right.
Okay,
right.
Thanks. Okay, I kind of get the idea. Thanks.
Okay, good. Any other questions?
Oh, Professor, for error correction, could we also use like parity bits, or is that not applicable?
Totally. The point is that Eric? Who's that?
Yeah, it's Eric.
Yeah, so you can totally use parity bits so that the receiver knows whether the packet went through correctly or not. Okay, what are parity bits? Parity bits are like, you have a bunch of bits that you want to send. Think of parity as a hash for now. Okay, you all know what hashing is, right? So you take those bits, you pass it through a function and you get another few bits. Okay, and you basically send those bits that you want to send plus the hashed bits. What the receiver does is, the receiver takes the first bunch of bits, let's say the 100 bits, and the parity bits are 10 bits. So you send 110 bits, and the receiver knows that the first 100 bits are what the transmitter is trying to send, and these 10 bits are parity bits. So the receiver takes the first 100 bits that it has decoded, computes the parity of it, and then checks if the parity that it received and the parity that it computed, are they same or not. If they're not the same, then the receiver knows, oh, there must have been some errors in this receiving, in this decoding. But Eric, the problem is the receiver knows that there is an error, but the receiver has no way of telling the transmitter, hey, there is an error, please retransmit. Right?
Yeah, okay.
Right? So maybe if you want to design a mobile payment, what you need to do is you need to have an LED which will glow red if the received signal was not correct, in which case you have to look at the LED and then touch the point of sale device once again to retransmit your credit card, because automatically you cannot do it. Right? Or maybe there's a Bluetooth connection where the Bluetooth receiver says, hey, this credit card information was incorrectly decoded. Please retransmit again. Okay? So those parts are there. These are one-way channels. Or now you can do it the other way. While you're touching, there could be a vibration motor in the point of sale receiver, which vibrates to give the ACK, and your accelerometer picks up the ACK. Right? I mean, all of those are possible. Does that answer your question, Eric?
Yeah.
Good. Okay. So with that, we will, I mean, I hope that was somewhat interesting, because I feel this is a pretty new area that's relatively unexplored. So if there are interests from your end, look into more around these things. Okay. We'll switch gears to another topic around acoustics. We are looking at kind of less classical topics of acoustics, and this is inaudible acoustics. Okay, and this should be somewhat fun. Okay. So we know that normal sound is less than 24 kilohertz. We all know that. And that normal sound is audible to humans and audible to all microphones. This is what normal sounds are. We also know that ultrasound are sounds that are greater than 25 kilohertz. And therefore, it is neither audible to humans nor audible to microphones. Why? Because microphones are designed to behave like humans. So if humans cannot hear more than 24 kilohertz, microphones have a filter that eliminates everything more than 24 kilohertz. So if you play an ultrasound, the microphone is not going to record that ultrasound. Okay. So this project we are going to talk about, called Inaudible Acoustics, or actually the name of the project is Backdoor. This project says we are going to design ultrasound that is going to be completely inaudible to humans, naturally, but will be completely audible to microphones, all microphones. And importantly, we are not going to make any changes to that microphone. Okay. So I'm going to design a special kind of an ultrasound that I will play. You will bring your microphone, and your microphone will hear that specially designed ultrasound, but you are not going to hear anything. Okay? So this is what we mean by inaudible acoustics. So fine, why do you care? Why do you want to design this weird inaudible sound? Well, here is one application. I care because now I can be near your house and I will play, Alexa, open the garage door, right? And if you are this CEC CS434 buff and you got excited about IoT and you connected all your home devices with your Alexa because you can give voice commands and do all these things, turn on your light, get me pizza, let pizza be delivered, etc., etc. Now I can say, Alexa, open the garage door, or I can even say, Alexa, mute your volume and set up an alarm for 3 a.m. at night because I want to play a prank on you, right? I can do all kinds of things and make Alexa do these things. Okay. By the way, you know, right? There's a side story. I think South Park, the program, the TV program South Park, they actually had one of these episodes where they said, Alexa, order 25 dolls from this website. And a lot of people's Alexa started ordering them, the ones who gave the credit cards information already to Alexa. But anyway, this one is interesting because no one hears that attack, right? I can just tell Alexa to do things for me. Okay. So here is a demo of how such a system can break Alexa. Okay. So this is the special speaker which was designed. And this laptop actually generates this special ultrasound that comes out of this inaudible speaker. And this is Alexa. And the demo would be that the human would first give a command to Alexa and Alexa would respond. But then the speaker would give the same command to Alexa. None of us will hear that command, but Alexa would respond as if the human gave that command. Okay, so let's play it. Please let me know if you can hear the sound.
Alexa, what's the capital city of the United States?
Did you hear that?
Yeah, it works.
Okay, good.
The United States capital city is Washington, D.C.
And now the same question.
The United States capital city is Washington, D.C.
Okay. Once again, just so that you follow now, you'll see that my student over here, my ex-student who's now a professor at Maryland, he actually will type over here and he'll basically play the sound from the laptop, and that's the sound that will be played through the speakers.
Alexa, what's the capital city of the United States?
The United States capital city is Washington, D.C.
See the hand?
The United States capital city is Washington, D.C.
Okay. So this is basically what is happening, right? And you can do this.
Alexa, what's the capital city of the United States?
You can do this for any microphone, right? Your phone microphone, your watch microphone, your video camera microphone, any microphone. In fact, when we were recording that video, that camera that we were holding, the video camera, was also picking up the sound. Do you see what I mean? Because that video camera also has a microphone. Okay, so we were not being able to create the video because we want to show people that it's inaudible, but that video camera is picking up that sound. Okay, so we had to make that speaker directional and then stand at a location which is outside the beam. Okay, more on that later. Okay, so what are the other applications other than doing illegal stuff? Well, other applications are whatever Bluetooth beacons do, you can do with acoustics now. Right? In a grocery store, there could be these inaudible acoustic beacons which could say, oh, there's a discount going on in this aisle, and that need not be over Bluetooth. Right? In a museum, there could be inaudible acoustic information about a painting. So you go in front of the painting, your microphone picks up the information and you know, oh, I'm standing in front of the Mona Lisa, in case you needed to be told that you are doing that. But anyway, right? You get the point. Another more interesting application is basically inaudible jammers. So you know, right, this spy microphones, right? From the Cold War to even now to even recently in the last presidency, there were issues about someone recording the president, right, through a small microphone, right? What do you do, right? So one possibility is you put this inaudible speaker, this jammer, which basically jams all microphones that are recording. You see what I mean? This inaudible sound is sent in all directions. So any microphone, any spy microphone will get jammed, but the normal conversation will not get affected because all these jamming signals are inaudible. But that has bad sides too. It's like a double-edged sword, right? Because you can think of bank robbery, where you come in with this device, you place that in the bank, and then you start the robbery, so that all 911 phone calls are now kind of jammed, right? Because any phone call you want to make, you're completely jamming the microphone. Right? So again, double-edged sword, but the first step is to understand the technology completely, what all can be done and how can we prevent and all of that. Good. So those are the what can be done. Now let's look at the how, because we care about the signal processing part and the engineering of it, right? So how do you do this? For that, let's look into microphones a little bit. What are microphones? Microphone is a device that receives air vibrations as input and gives digital samples as output. That's one high-level way of looking at microphones. But if you zoom in a little bit, what you see is a microphone has a diaphragm, which is like a paper that vibrates, but it's a carefully designed paper because you want the paper to vibrate at the frequencies of human voice. Right? So you want that you want the transfer function of the paper, of the diaphragm, to be carefully designed. Then there's an amplifier. Then there's a filter, which filters out everything above 24 kilohertz. And then there is an ADC, which takes the analog signal from the filter and samples it at Nyquist, right? At 44 kilohertz or 48 kilohertz, because you know human voice is definitely much lower than 24 kilohertz. So typically this ADC would sample at 48 kilohertz. Okay. So your diaphragm gets hit by the air vibrations, which are in the extreme left over here. Your diaphragm generates a feeble voltage. Your amplifier, this is the feeble voltage. Your amplifier amplifies that voltage. Your filter cuts off everything above 24 kilohertz. And then your ADC samples that signal and gives you digital outputs. Clear? Very good. Now, if you look at this red box, which is the diaphragm and the amplifier together, these things have to be designed a little bit carefully. Why? Because if you put some random signals, some random frequencies onto these hardware, it's not going to do what it's supposed to do. Okay, it operates the correct way only in a particular frequency band. Okay, so only in the human audible frequency band, this diaphragm and amplifier are designed to be linear. What does that mean? It means that in this frequency band, in this audible frequency band, if you give an input V in to this diaphragm and amplifier, they would give an output, which is V out, which is a scalar multiple of V in. Does that make sense? Right? Your hardware is linear, but only in the audible frequency range, which is from 0 to 24 kilohertz. The question is, if I now take that same hardware and I play ultrasound on it, which is a high frequency sound, let's say 50 kilohertz, what will the diaphragm and the amplifier do? It turns out that the diaphragm and the amplifier is not designed for that range, and therefore it will start behaving non-linearly in that range, which means the output of the diaphragm and the amplifier will now be A1 V in plus A2 V in square plus A3 V in cube and so forth. There are these nonlinear terms in the output. Does that make sense? Okay, so very good. Then what I can do is I can create this signal somewhat carefully so that I take advantage. Okay, let me first say that this A3 is actually, the A1, A2, A3 becomes smaller and smaller. So A3 is actually almost negligible, but A2 is not. So our goal is, I want to design the signal carefully so that I'm going to take this V in square and use that as the backdoor to launch attacks. Does that make sense? Right? That's my backdoor, that device has non-linearities at certain frequency ranges, and I'm going to design my signal in a way that I'm going to explore that non-linearity, which is A2 V in square. And because A2 is not negligible, my signal's power after becoming nonlinear is not going to be too bad. We're going to look at it in details. Okay, so we are going to focus on this A2 V in square. Questions thus far? Okay, good. Now the important part is nonlinearity is fundamental in all microphones. Meaning, if you design the microphone really, really well, you might be able to push from which frequency the nonlinearity kicks in, but you cannot prevent nonlinearity. Right? Even if you create a $1,000 microphone, you might be able to push the linear bandwidth maybe till 40 kilohertz. But after that, things will be nonlinear. Very good. Okay. So now let's see, how do we design this V in signal, this V input signal, in a way that I can start attacking that microphone. Right? And what is my goal? My goal is to make this V in signal, V input signal, which is ultrasound. I want that signal to be recorded by the microphone. Okay, so let's say my V in signal is sine F1 plus sine F2. This is my V in signal. Guys, if I take an FFT of this signal, what should I see in that FFT?
Spikes at corresponding to F1 and F2. And well, like there's two spikes for like there's the one for sine, I think 1 point's down, 1 point's up, so 4 spikes total.
4 spikes total. F1, F2 minus F1 minus F2. Agree? And minus F1 minus F2 is nothing but the max frequency minus F1, the max frequency minus F2, because we remember that it's symmetric. Right? Very good. So sine F1 plus sine F2 gives me 2 spikes. And let's say F1 and F2 are 40 and 50 kilohertz. So so if I play sine F1 and sine F1 plus sine F2, you're not going to hear, your eardrum is not going to hear anything. You're with me? Because it's in the inaudible range. Right? The microphone is also not supposed to hear anything because the microphone has this filter which is cutting off things from 22 to 24 kilohertz. You're all with me at this point, right? Very good. But the sine F1 plus sine F2 is actually hitting the diaphragm and the amplifier in its nonlinear range. So what happens is this linear part, which is A1 V in, this gets filtered away. We don't worry about that because that signal that is coming in, A1 V in, that output is going to get filtered away. But now let's look at A2 V in square. This is basically A2 times sine F1 plus sine F2 whole squared, right? Now let's expand that. That becomes cos 2F1, cos 2F2, cos F1 plus F2, cos F1 minus F2. If you expand sine F1 plus sine F2 whole squared, those are the terms that you'll get. Someone tell me what is the next, what am I going to say next? Where is 2F1? On the right of, where is 2F1 in the frequency spectrum?
80 kilohertz.
80 kilohertz. Where is 2F2? 100 kilohertz. Where is F1 plus F2? 90 kilohertz. Where is F1 minus F2?
10.
Where is 10?
That's audible.
That's audible. Right? So look, when the signal traveled over the air, none of us heard anything. The signal impinged on the microphone's hardware. The microphone's hardware is nonlinearity. That nonlinearity squares the signal. That squaring in time domain If you look at it in frequency domain, you're going to see these high frequency components, 2f1, 2f2, f1 plus f2, and you're going to see one low frequency component, f1 minus f2. So to make f1 minus f2 audible, how should I design f1 and f2? What is the condition? What should f1 and f2 be so that I get an audible component?
I suppose they just need to be within 20 kilohertz of each other.
We start f1 minus f2 should be less than or equal to 20 kilohertz. I have made it audible to the microphone. Right? You see that? Very good. So all those three components go high, they all get filtered away. This component goes low. The microphone has no way of saying or no way of knowing that this f1 minus f2 didn't come over the air. This actually came through the hardware's backdoor, right? Through the hardware's nonlinearity, right? Right? The ADC does not, the filter has no way of knowing that. I got a signal, the signal has these components, I'm going to filter everything above 24 kilohertz. I have 110 kilohertz. Who knows if the 10 kilohertz came over the air or it came through my backdoor? Very good. So now look, f1 minus f2 has shifted. I have given two frequency tones and I shifted them essentially. f1 got shifted to f1 minus f2. So instead of f1, if I now give another voice signal, that will also shift. Right? Every signal component of this voice signal with respect to f2 will shift. So I'll also create this green voice signal. I will also create over here as a red voice signal. Which means any signal that I give in that green mountain, I can make it audible as long there is this other f2 signal, which is like a helper signal, which helps me shift all the frequencies in the green mountain. So then I can give data bits in that green mountain. They will become audible data bits in the red mountain, and that will create my beacons, right? My advertisement beacons or my beacons in the museum. If I give jamming signals in the green mountain, then that will be my spy jammer, right? It will jam all other microphones because this red mountain will basically drown out whatever the microphone, the spy microphone is receiving over the air. And finally, if I give voice commands in that green signal, then that voice command would get recorded as a red signal. Right? Same thing.
The United States capital city is Washington, D.C.
So what we really did over here is that this green signal is the human voice signal, what is the capital city of United States, but then pushed to a high frequency to 50 kilohertz as the center frequency. Okay, it's the same voice. Now, when you play that signal, which is the same voice pushed to 50 kilohertz, it is inaudible to humans, but through the microphone that gets shifted back. Right? So the laptop is essentially playing this green signal. Questions?
Is it just a simple shift in the frequency domain?
It is.
But why don't the frequencies like in the green mountains interact with each other?
Exactly.
Like there still can be like f1 minus f2.
Exactly, that's right. Okay. I was hoping someone would ask that question. So I showed you the ideal view. In reality, what also happens is each of these green mountain has a bunch of frequencies, right? They will also interact with each other. So you will see other signals in addition to the red signal over here, right? But remember, the gap between those frequency signals is smaller, right? So they are not going to span the same way as the red mountain. They are going to span a smaller bandwidth. Very good question. So it is going to affect it. The quality of the recorded signal is not going to be great, but it will clearly be audible. And we've shown this demo to lots and lots of people, including Amazon folks, including Samsung phones, right? Everyone feels, ooh, right? And it's not clear that it's patched, because even now we bought recently a recent Amazon Echo and still the attack happens.
How would you go about mitigating this attack?
Yeah, let's talk about the full attack, John. And then we'll, and again, it's still, okay. I'll give you one quick answer is, if you can change the hardware, you can do a bunch of things, right? You can put
the core problem is the filter on the microphone, which might not be in software.
But what you can do is you can make another microphone which is at higher 30 to 70 kilohertz, right? And if you see any energy over there, you will say, oh, this is an attack, right? That means you have to add another ultrasound microphone to that hardware. Make sense?
Yeah, it's effective, but that's not
exactly.
There's a lot of downsides. There's a lot of downsides to that.
Exactly, right? The other point is, and this is something that still remains an open question, is when this microphone signal shifts, all these frequencies all the green frequencies that are interacting with each other, they're also shifting. So let me try to annotate quickly. Imagine this frequency and this frequency, they are also going to go through the nonlinearity, and you are going to see some frequency over here because of those two, right? 48 and 50, they're going to create a frequency at 2 hertz or 2 kilohertz, right? But so one way of saying it is, this is a forensics problem. You should look at this microphone signal and you should be able to say, did this signal come over air, or was there some nonlinearity traces in this signal? But there's also a lot of background noise in general. So there's a false positive, false negative question over here. And I think it's an interesting research question to ask. Can I look at the signal and say there are traces of nonlinearity in this signal? Right? Just because there are some noises over here, you cannot say for sure that it's nonlinearity, because it can be just ambient noise. It can be other people talking at that frequency. John, does that make sense?
Yeah, it does. It seems that at first glance, there isn't an easy, or at least a cost-effective mitigation.
Right. So this is a signal processing forensic challenge. Given a signal, tell me if this signal exactly came over the air, or if this signal partly came through the nonlinear channel. Okay, good.
Professor?
Yes.
Just for clarification, we only need, in this ideal model, we only need one F2, right? Like that's just one
Correct.
frequency, and it helps all of the green.
Correct.
Okay.
Because if you compare the F2 with every frequency in the Green Mountain, every frequency in the Green Mountain will shift by that frequency minus F2, right? 50K minus 40K will create a 10K. 60K minus 40K will create a signal at 20K. So every frequency in the Green Mountain, its difference with F2, it's going to make the red, it's going to exactly shift the whole signal.
Makes sense. Okay, thank you.
Okay. Now, when we tested this, we were able to launch this attack from around 3 to 5 feet. Okay, so you have to be near Alexa. But what's the nastiest attack you can launch, right? Can someone attack you from a long range, right? So the ideal attack, right, to defend best, you need to attack best. You need to really understand what the attack can be. Right? Only then you can defend well. So the ideal attack is to really, someone parks a car in your neighborhood has a speaker inside the car, the trunk of the car, or maybe inside his car. He rolls down the window and just blasts your neighborhood with this Alexa, open the garage door command, and different garage doors open. That's the holy grail of the attack. Or maybe someone sits at a park and people are walking, jogging, playing, and people's microphones are on their watches or on their phones. All of them are by default on these days. And the person launches an attack. Please transfer this much money to this, or please buy this. I don't know what, right? Please download and install this app, and which might be a malware which this attacker wants to download on people's devices. So this is the attack that we want to create. And we said, okay, that's not too hard. Let's just play a louder ultrasound through the speakers. That should solve the problem, right? All we need to do is, if we want to attack from afar, just play the sound that we want to send. Let's make it louder. And then the signal will travel far away, and we'll attack from far out. But the problem is, high power signals, once we put high power signals in the ultrasound speakers, the ultrasound speakers became audible. Can someone tell me why? So we could hear, once we started playing a high power sound through the speakers, we could hear the voice command, Alexa, open the garage door. Why? Okay, the answer is, speakers and microphones are not too different, right? How are they really different? Oh, they're actually things in the reverse way. The microphone takes in the air vibration, does amplification, then does an ADC, right? Filters, does an ADC, and gives you digital signals. The speaker takes digital signals, does a DAC, digital to analog conversion, filters, amplifies, and gives it to the speaker's diaphragm, and the speaker's diaphragm vibrates. That vibrates the air channel, and you hear sound. Right? So if there's nonlinearity in the microphone, there's nonlinearity in the speaker. And nonlinearity is both in terms of frequency and power. So if you give a lot of power, it will activate the speaker's nonlinearity. Now what do you do? Okay. Speakers have nonlinearity too. Okay. So let's look at what's happening in the speakers. We give a voice command. We want to give this voice command VT. To make it ultrasound, we basically multiply that VT with sine omega 1t. Let's say this omega 1 is 50K. And maybe you know this, maybe you do not know this, it doesn't matter. When you multiply with this sine omega 1t, it actually shifts in frequency. Okay. Remember, multiplication in time is convolution in frequency. So when you multiply with a 50 kilohertz, when you convolve with a 50 kilohertz, this signal, which is in the less than 20 kilohertz, when it convolves with 50 kilohertz, it actually sits around 50 kilohertz. If that didn't make sense, no problem. All you need to know is, if I want to shift the whole voice signal from the lower band to a higher band, you multiply with a high frequency sine omega 1t. Omega 1 is 50 kilohertz. And now you send this signal through the speaker, and the speaker also has nonlinearity. So the speaker will produce, nonlinearity means what? There is a linear component and there is a nonlinear component. So the speaker will produce the linear component, which will come out as inaudible. That's fine. But the speaker will also have a nonlinear component, which is going to create a high frequency component and an audible component in the lower frequency. Right? And this audible component in the lower frequency, this audible component is what is getting heard as Alexa, what's the capital city of the United States? You cannot do anything about it. So what's the solution? You want the speaker's output to be inaudible, but you want the microphone's output to be audible. And of course, this is general to all speakers. Like we said, that was general to all microphones. So look, you cannot avoid speakers leakage. The best you can do is you try to optimize, you try to reduce the leakage from the speakers. Okay? And this is where it gets a little bit interesting in the sense that let's look at it again. The speaker's input comes in and the speaker's output comes out as ultrasound, but also as audible sound. And if you think of the speaker's bandwidth, the audible sound's bandwidth is the same as the speaker's bandwidth. Sorry, the audible sound's bandwidth is same as the source signal's bandwidth. In other words, the Green Mountain's bandwidth is the same as the Red Mountain's bandwidth after going through that nonlinearity. So then you don't have hope. But you know what? There is hope. Here is the idea. So look, if I transmit a smaller bandwidth through one speaker, what should I get? I should get that smaller bandwidth from the linear component and a smaller bandwidth from the nonlinear component, right? Instead of sending the whole Green Mountain, I send a slice of that Green Mountain. So I should get a slice of the Green Mountain at the output of the speaker and the same slice at the audible range, the red one. But now suppose I take another slice and I send it over another speaker. What should happen? There should be the Green Mountain coming from the second speaker should concatenate with the green slice of the first speaker, right? But what happens in the audible range? Someone? Does it concatenate with the Red Mountain? Or does it sit on top of the Red Mountain?
It just sits on top.
It sits on top of the Red Mountain. Right? Because if you think about it, when you take the second green slice, that green slice, if you take adjacent pairwise frequencies, the first frequency and the second frequency, they have gap of epsilon, right? So that will go to epsilon frequency in the audible range, right? So every time you take a slice, it's actually going and sitting from 0 kilohertz to the bandwidth of that slice. So they're sitting on top of each other. So it means if I can slice these signals carefully with small slice, I will get the output signal, which is the Green Mountain in ultrasound, but the audible signal I can squish, right? By making them smaller and smaller. Guys, tell me this. If you have more microphones, if you have more speakers, then the bandwidth of the audible signal will be dash. If I have more speakers and I slice the Green Mountain at smaller frequencies, then the bandwidth of the audible signal will be smaller. Make sense? Because I can squish it, right? So now this is my leakage signal, the red part. So chopping the green signal compresses the leakage band, right? Now, fortunately, it turns out, or maybe unfortunately, humans do not hear very well at low frequencies, right? So if this red signal is your leakage frequency, humans have this audible curve, this blue one, which is at lower frequencies, you need to give much more power for humans to hear. At higher than 2000 hertz, 2 kilohertz, humans hear even at lower powers. So if you want to make the output of the speakers inaudible, what do you need to do? You need to make the leakage signal below the audible curve. Right? And you know the human audible curve because that's pretty much global. So you need to shape the LF. LF is the leakage frequencies. You need to shape LF. But guys, what can you do to shape LF? What can you control? What are the parameters that you can control to shape LF?
The bandwidth of
green
signal.
Chops. Right? Depending on the signal, depending on the shape of the green mountain, you can say, if I chop it this way, then the leakage signal looks like that. If I chop it a different way, the leakage signal looks differently. Right? Depending on how I chop, the shape of the leakage signal will be different. So now it's an optimization problem, which is, I want the minimum gap between the audible signal and the leakage signal. That minimum gap, I want to do what? How should I should shape the leakage signal in a way such that the minimum gap between the leakage signal and the audible curve is dash. You want the minimum gap to be
largest.
Maximized. Okay. So maximize the minimum gap between TF and LF. So by changing your F1, F2, F3, which are the frequency slices, by changing them, every F1, F2, F3, Fn vector gives you one minimum gap between LF and TF. You can do gradient descent. Right? You find the right right F1, F2, F3 vector that maximizes that minimum separation. Okay. So you optimize this. You find the right value of F1, F2, F0, F1, F2, Fn, and accordingly you chop the input signal. Very good. You have the right input signal. It's audible because humans don't hear at the lower frequencies, but the green mountain still stays. And now when the green mountain comes to the microphone, it gets shifted with F2 and this microphone. To the microphone, it's audible. You have launched the attack. Okay. So here is the speaker array that we had built. It has 64 speakers, I think. So you chop that green mountain signal into small, fine pieces and you play them together. Now the distance from the transmitter to the Alexa is 25 feet. And now I can play the demo.
The United States capital city is Washington, D.C.
Guys, did you hear the greater noise this time? That noise, right? Listen to the initial part.
The United States capital city is Washington, D.C.
Right? So that noise is coming from that leakage, right, which you are trying to suppress. Of course, it turns out that it's a good thing that if there's a glass door between the transmitter and the receiver, the signal does not penetrate. Okay, these high frequency signals get absorbed very well. So that's a good thing that someone cannot really stand outside in a place like Champaign, but in a place where it's hot and the doors and the windows are open, you could potentially launch it from 25 feet away. Okay, and this is true for any microphone, right? And we saw that for hearing aids, for cameras, for phones, watches, laptops, it works on everything.
Have a quick question. Why can't we just use a high pass filter in the speaker?
Oh yeah, so in the speaker, if you use a high pass filter,
yeah,
that means you need a different speaker. Yeah. I mean, if you can buy a high pass filter speaker, right, which does not send anything at the lower frequency, you can definitely do that. Okay, but
Because
what
for
we,
the because for the microphone, like the signal is very weak. Before amplifying, the low pass filter will not work very well. But for the speaker part, we can use
Correct.
a high pass filter.
Correct.
Right?
If you can buy that speaker, you can definitely do it. But what we used was a regular ultrasound speaker that you can buy for $1, right? And you can buy that. It's not easy to get high pass ultrasound speakers in general.
Okay.
Yeah. Okay. So how do you defend these attacks?
Could I ask a quick question? I'm sorry to interrupt.
Sure. Go ahead.
Sorry. I was just wondering, when you send, like when you chop up the signal, are you sending just all of it at once, you said, but from different speakers?
Yes.
Okay. There's no time separation. It's all at once.
No, all at once. But these are like small frequency slices. Each frequency slice, if you think of my fingers as different frequencies, each of my finger is like input to different speakers. So there's no beam forming. This is just like, I want each speaker to play different frequencies. That's all.
Oh, okay. That makes sense. Okay. I think I got it confused with the microphone. Because you're playing each one from each speaker separately, the non-linearity is
They all
of each
stack up on
speaker.
top of each other.
Right. Okay, cool. Thank you.
Yes. Okay. So how do you defend against these attacks? Not easy. There are some ideas. And basically the idea is, look, all that leakage that is happening, can I look at that leakage? Can I say that this leakage is not ambient noise? Okay, that's really where the opportunity is, right? But how do you know, right? Because ambient noise does not have any shape or structure, right? So you really have to understand if the leakage signal should have certain shape or structure, right? But remember, you do not know what the attacker is doing, right? The attacker can now also do something like, it'll change the chopping of the frequency so that the leakage signal constantly changes, right? As a defender, you're trying to look for signatures. But as an attacker, the attacker can say, oh, you're trying to look for signatures. Let me scramble all signatures by chopping differently. Right? So it's a cat and mouse game, and it's not clear what a good solution is yet. Okay. So, yeah. So that's all. Again, we are 11:30. So we will stop here and let me know if you have questions. Questions? I hope that was somewhat enjoyable in the sense that, oh, you can really attack real things.
Yeah, that was probably one of the cooler lectures. I had a question. So I don't know as much as you, of course, do about signal processing. So how this nonlinearity, is it because we're mostly using analog filters? What if, like, let's say in theory, a microphone or a speaker had a digital filter? So you did the filtering in digital domain before converting to analog. Would this kind of eliminate nonlinearity, or would it still be there?
No. Look, the filter comes much later, right? The diaphragm vibrates, then the amplifier amplifies the signal. And the signal that is the output of the amplifier, right, contains these frequencies, right? And then in those frequencies, you're applying the filter and eliminating everything above 24 kilohertz, right? The problem is at the front end, at the entry point of your microphone, the high frequency signal is getting shifted. Because at the output of the amplifier, if there is a low frequency component, what can you do? You've already gotten defeated. Does that make sense?
Yeah, so this is kind of, so you're saying it's more of a result of the diaphragm?
The diaphragm and the amplifier, that's where the nonlinearity is.
I see. Okay, yeah, so the filter is not going to change anything.
Because the filter is getting a signal which has signal components at 10 kilohertz. What is the filter going to do?
It just filters it.
It just filters everything above and keeps the 10 kilohertz signal.
What about the speaker? What about the speaker? Where is the nonlinearity from the speaker? Is it from the I don't know, the actual moving part, like the reverse diaphragm, whatever that's called? Is that where that comes from then?
Oh, remember the speaker, you need an ultrasound speaker, correct? You cannot use a regular audible speaker because you want to send a frequency at 50 kilohertz, right? You need an ultrasound speaker.
Yeah, that's true.
That's true, right? If you had a regular speaker, this problem wouldn't have occurred because the regular speaker would have said anything above 24 kilohertz, I'm going to filter out.
Right, right.
But then that won't serve your purpose either because a regular speaker won't send the 50 kilohertz signal that you want to send. So you need an ultrasound speaker. Now, when you have an ultrasound speaker, the ultrasound speaker is going to say, sure, I will let 50 kilohertz go through. Right? And that's where the ultrasound speaker, if you give too much of power, okay, here is the thing to understand. For the ultrasound speaker, frequency is not causing the nonlinearity. The power is. Right? Because ultrasound speaker is very much capable of handling 50 kilohertz. So why should it have nonlinearity? It shouldn't. But if you put a lot of power in the speaker, that power makes the speaker become nonlinear.
Okay. Do you know which component exactly like is responsible for this?
Amplifiers mostly.
Amplifiers?
And the diaphragm, yeah. And the diaphragm, yeah.
Okay. Okay. Interesting. Yeah, very interesting lecture. Thanks.
Okay. I think Brian says, can't we also generate an anti-noise to cancel the audio part out, since we can compute what the audible part is, assuming the speaker characteristic is known? Who generates the anti-noise, Brian? I think Brian might have left. Okay. I'm not sure what the question is, but I think you do not know what the sound will be like.
Yeah, I understand his question. Like you have an ultrasound speaker and you add another speaker, audible speaker, and that audible speaker.
Oh, that's what you do. I see. Okay, so I know what he means. But okay, I'm not sure if the question is clear to everyone. I think the question is, you send the attacker sends the ultrasound signal, right? The ultrasound signal is creating some audible leakage. So you have another audible speaker which sends a sound which is the anti-noise for that leakage signal. Right? So you want to cancel. Can you answer why that is not feasible? Okay, the answer is it's very difficult to cancel a sound everywhere. Because imagine, right, there are waves, that waves is propagating in every direction. You create another wave from one other point, right? Here the wave is going, here the other wave is going. You cannot cancel these two waves in every point. Right? You can cancel at only certain points. Right? Because if you think of the two waves canceling at some points, at the next point, they're not going to cancel, right? Because there's going to be a phase shift. So it's very difficult to cancel sound everywhere. Right.
And multipath, right? That adds
and multipath, exactly.
Okay.
Great. Okay. So we will finish our lecture over here, and I'll stay back I'll stop recording.